There is also the less obvious question, how are all the various letters in a single typeface related to each other? This is a grand analogy problem if ever there was an analogy problem. One is asking for a B that is to the abstract notion of B-ness, as a given A is to the abstract notion of A-ness. You have to take the qualities of a given A and, so to speak, hold them loosely in your hand as you see how they slip into variants of themselves as you try to carry them over to another letter. Here is the very hinge point of thought, the place where one thing slips into alternate subjunctive variations on itself. Here, that thing is a very abstract concept, namely the way that this particular shape manifests the abstract quality of being an A. The problem of A is thus intimately connected with the problems of B all the way through Z, and with that of stylistic consistency. The existence of optical character readers, such as the reading machines invented by Ray Kurzweil for blind people, might lead one to believe at first that the letter recognition problem has been solved. If one considers the problem a little more carefully, however, one sees that the surface has barely been scratched. In truth, the way that most optical character recognition programs work is by a fancy kind of template matching, in which statistics are done to determine which character out of a fixed repertoire of, say, 100 stored characters is the best match. This is about like assuming that the way I recognise my mother is by comparing the scene in front of me with stored memories of the appearances of tigers, cigarettes, hula hoops, gambling casinos and can openers, and of course all the other things in the world simultaneously, and somehow coming up with the best match. Although, let's face it, it's not really like that, is it, Hofstadter? It's really like you comparing a picture of your mother to a picture of every other human being that you've met. I mean, you don't compare mothers and hula hoops, or mothers and cigarettes. You might compare mother and sister, or mother and teacher, but anyway. The human mind and its ability to recognise and reproduce forms. The problem of recognising letters of the alphabet is no less deep than that of recognising your mother, even if it might seem so, given that the number of Platonic prototype items is on the small side, i.e. 26, if one ignores all characters but the lowercase alphabet. For example, one can even narrow it down further to just a handful. As a matter of fact, Godfrey Toussaint, editor of the pattern recognition papers for the IEEE transactions, has said to me that he would like to put up a prize for the first program that could tell correctly, given 20 characters, that people easily can identify which ones are A's and which ones are B's. To carry out such a task, a program cannot just recognise that a shape is an A, it has to see how that shape embodies A-ness, and then, as a test of whether the program really knows its letters, it would have to carry that style over to the other letters of the alphabet. This is the goal of my research, to find out how to make letters slip in similar ways to each other, so as to constitute a consistent artistic style in a typeface, or simply a consistent way of writing the alphabet. By contrast, most AI work on vision pertains to such things as aerial reconnaissance or robot guidance programs. This would suggest that the basic problem of vision is to figure out how to recognize textures and how to mediate between 2 and 3 dimensions. But what about the fact that, although we are all marvellous face recognizers, practically none of us can draw a face at all well, even if someone we love? Most of us are flops at drawing, even such simple things as pencil in hands and books. I personally have learned to recognize hundreds of Chinese characters, shapes that involve neither 3 dimensions nor textures, and yet, on trying to reproduce them from memory, find myself often drawing confused mixtures of characters, leaving out basic components, or worst of all, being unable to recall anything but the vague feel of the character, and not being able to draw a single line. Closer to home, most of us have read literally millions of, say, U's with serifs, yet practically none of us can draw a U with serifs in the standard places, going in the standard directions. This holds even more for the kind of G you just read, the G with 2 circles. But it is true for any letter of the alphabet. I suspect that many people, perhaps most, are not even consciously aware of the fact that there are 2 different types of lowercase a and of lowercase g, just as many people seem to have a very hard time drawing a distinction between lowercase and uppercase letters, and a few have a hard time telling letters drawn forward from letters drawn backwards. How can such a fantastic recognition machine as our brain be so terrible at rendition? Clearly, there must be something very complex going on, enabling us to accept things as members of categories and to perceive how they are members of those categories, yet not enabling us to reproduce those things from memory. This is a deep mystery. In his book, Pattern Recognition, the late Mikhail Bongard, a creative and insightful Russian computer scientist, concludes with a series of 100 puzzles for a visual pattern recognizer, whether human, machine or alien, and to my mind it is no accident that he caps his set off with letter forms. In other words, he works his way up to letter forms as being the pinnacle of visual recognition ability. There exists no pattern recognition program in the world today that can come anywhere close to doing those Bongard problems, and yet Barr cites Simon as writing the following statement. The evidence for that commonality between the information processes that are employed by such disparate systems as computers and human nervous systems is now overwhelming, and the remaining question about the boundaries of cognitive science have more to do with whether there also exists non-trivial commonalities with information processing in genetic systems than with whether man and machines both think. Wherever the boundary is drawn, there exists today a science of intelligent systems that extends beyond the limits of any single species. I find it difficult to understand how Simon can believe this. In an era when computers still cannot do basic kinds of subcognitive acts, acts that we feel are unconscious, acts that underlie cognition. In another lecture in 1979, the opening lecture of the inaugural meeting of the Cognitive Science Society, also in San Diego, I recall Simon proclaiming that, despite much doubting by people not in the know, there is no longer any question as to whether computers can think. If he had meant that there should no longer be any questions about whether machines may eventually become able to think, or about whether we humans are machines in some abstract sense of the term, then I'd be in accord with his statement. But after hearing and reading such statements over and over again, I don't think that's what he meant at all. I get the impression that Simon genuinely believes that today's machines are intelligent and that they really do think or perform acts of cognition, to use a bit of jargon that adds nothing to the meaning and makes it sound more scientific. I will come back to that shortly, since it is in essence the central bone of contention in this article. But first, a few more remarks on AI domains. Toy domains, technical domains, pure science and engineering. There is in AI today a tendency toward flashy, splashy domains. That is, toward developing programs that can do such things as medical diagnosis, geological consultation for oil prospecting, designing of experiments in molecular biology, molecular spectroscopy, molecular spectroscopy, I can't pronounce that word, spectroscopy, bollocks, configuring of large computer systems, designing of VLSI circuits, and on and on. Yet there is no program that has common sense, no program that learns things that has not been explicitly taught how to learn, no program that can recover gracefully from its own errors. The artificial expertise programs that do exist are rigid, brittle, inflexible. Like chess programs, they may serve a useful intellectual or even practical purpose, but despite much fanfare, they are not shedding much light on human intelligence. Mostly they are being developed simply because various agencies or industries fund them. This does not follow the traditional pattern of basic science. That pattern is to try to isolate a phenomenon, to reduce it to its simplest possible manifestation. For Newton, this meant the apple falling and the moon. For Einstein, the thought experiment of the trains and lightning flashes. And later, the falling elevator. For Mendel, it meant the peas, and so on. You don't tackle the messiest problems before you tackle the simpler ones, and you don't try to run before you can walk. Or, to use a metaphor based on physics, you don't try to tackle a world with friction before you've got a solid understanding of the frictionless world.